Alright, my lovely, brilliant, and perfect AP Physics students who almost made Miss Benjamin cry in a good way. Let's get started looking at position, distance, and displacement. If you did not follow the instructions I gave in class and have not yet read the 2 pages from the textbook that I gave you on Friday, do that now. Stop the video, go read those 2 pages. Even if you are a little unsure about some of the words, struggle through those 2 pages, and then I'm going to talk through them with you. Alright, hopefully you have read those 2 pages now. I'm just going to talk through them. The textbook does a really good job at explaining this concept. So have that page with you as you watch this video. We're just going to go through it. First up, most important thing in understanding position and displacement is setting up a coordinate system. Now this might seem like an unfamiliar intro to people who had me last year because we didn't go this deep into how position, distance, and displacement work. So in the first example in the book, which I think is a pretty good one, they set up a coordinate system. And in any coordinate system, you have to define what's called the origin. The origin is the place where x equals 0. Now you might be wondering why I'm saying x equals 0. X is the customary variable for distance and displacement in physics. If you take college physics, displacement will eventually come to be called r, but for what you need to know now, we can treat distance and displacement as x. Alright, so anytime I want to talk about where something is, so let's say I have a person. Also, sorry about that, I decided to switch colors. And I want to locate that person. Well, you wouldn't just point to somebody and say he's there in physics. You've got to say there in relation to something else. He's 5 meters from the door. He's 12 miles from my house. You got to relate it to something. And whatever that from is, like where I said 12 miles from my house, in that case I use my house as the origin. Now, in general, so without using numbers, we can define a person's starting position from the origin as xi, or the initial x position. Don't know how to get this computer to let me do subscripts. I'll show you what a subscript is. So I typed xi, but with a subscript it would look like this. So x, not x times I, it shouldn't really be x underscore I. That I is a subscript. So read any x underscore I as x subscript I. Anyway, we would define a person's starting position relative to the origin as xi. Now what might seem strange about that is you might expect the person's starting position to be at the origin, but that's not required. We can declare our origin anywhere we want. And then we talk about a person's starting position as xi. If that person moves to somewhere else, the position where they end up is called their final x position, or xf. Okay, so final position, xf, or x final. Probably picking up that the subscripts are just the first letter of whatever the x is all about. Alright, now in general you also indicate a positive direction on your coordinate system. So remember I had to set up a coordinate system. The arrowhead at the end of the coordinate system usually indicates positive direction. Sometimes we'll have multiple arrowheads, we'll get to that later. So our positive direction on this graph is this way. That's an arbitrary choice. It means that the choice doesn't matter. I could have called left the positive position. I've just chosen to call right the positive position. It doesn't matter. All the mathematics and all the physics will still be the same. Now right now we can say a couple things about these 2 positions. For example, xf is farther from the origin than xi. So we can say the final x position is greater than initial x position. That's just one basic statement we've made. Alright, so that's a long explanation for something that hopefully does seem pretty simple, but I want to make sure you have a really deep understanding of setting up coordinate systems. That textbook page I gave you, has really great definitions of distance and displacement, which are what I'm about to talk about. So in your notes, go ahead and copy over those definitions. They have lines right beside them. So for example, in the textbook page I have, it says definition distance. Distance equals total length of travel. SI unit is meters represented by m, so or meters comma m. Like I said, copy down those definitions from the textbook. They are really great. In the definitions, though, you're going to come across this term SI unit. SI stands for the French phrase Système International d'Unités, which roughly translates to the International System of Units. The metric system is part of the International System of Units. It is not the full thing, but for now you can pretend that SI and metric system mean the same thing. So the metric unit for distance, meter. The metric unit for distance, for displacement, is meters. Alright, in the example, there are 3 buildings. Your friend's house, your house, and the grocery store. And first, the textbook talks about distance. In this question, or in this example, it says, let's suppose we go to the grocery store from your house. Well, they also give us some distances. Friend's house to your house is 2.1 miles. Your house to the grocery store is 4.3 miles. In the question, you go from your house to the grocery store and back to your house. First example is just dealing with distance, and that has nothing to do with direction. So this first trip is 4.3 miles. Second trip is 4.3 miles. Total distance, if I add them up, is 8.6 miles. Right. Next, they give you an example for displacement. Well, I can tell you right away your displacement is 0 because you start and end at your house. Your change in position is 0. If just getting that intuitively, if you're not there yet, let's confirm it mathematically. Change in position or displacement is final position minus initial position. Well, if my friend's house is at the origin, as they have in the textbook, notice that it says your friend's house is x equals 0, then I can assign numbers to every other building. My house is now at x equals 2.1 miles. So, I can go down here and put in that in final x position is 2.1 miles, minus initial, which is also 2.1 miles. Anything minus itself is 0. My displacement is 0. My distance is 8.6 miles. Be sure to go ahead and read through the next few paragraphs. They've got some neat examples that demonstrate how distance and displacement are not the same thing and can end up as very different things. So even if you read it once before, now that you've gotten my explanation of the first example, go ahead and pause the video and read those next few paragraphs again. After you've done that, when you're ready, come back. We'll do another slide that walks you through a couple more things. Alright, I've changed the slide up a bit to talk through the next couple of things. Once you have read through those next few paragraphs, I want you to try the active example by covering up their answer on that right-hand column. So they give you the question, and then they give you the answer on the right. Cover that up. Try both parts A and B. One thing you need to note is where you get the numbers for this problem is by flipping the page back to figure 2.2, where it shows friend's house, your house, and the grocery store. So the numbers for this problem come from there. Try it, and then check your answer with what it has in that right-hand column. Once you've done that, try the your turn problem. Now this one is really interesting because what they ask you to do is instead of having your friend's house be the origin, they label your house as the origin. I'm going to write this in red to show it's different. So your house is now the origin. And you're going to do the math that you just did in those last two active example, part A and B problems, again, but now do it with your house as the origin. So take a couple minutes and do that, and then come back and I'll walk you through it. Alright, so the your turn problem says that we are going to go from your friend's house to the grocery store, and then back to your house. Alright? Now a couple things to note is now that your friend's house is to the left of the origin, it is located at position x equals negative 2.1 miles. Now, when we're answering the distance part of this problem, distance has nothing to do with direction. So let's just divide up our trip into easy parts and figure out how far we went. Okay, so this first part of the trip, from the beginning of the orange line to that blue line, is 2.1 miles. Remember, distance has nothing to do with direction. The second part is 4.3 miles. And the final part is 4.3 miles. Okay, now you just add up all those distances, and you should get 10.7 miles. Now we want to know the displacement for the trip from your friend's house to the grocery store, and then to your house. So we're going to do that same process again. I'm going to do it the mathematical way, and then I want you to look really carefully at what I've drawn here and convince yourself that my mathematical answer is correct. So I'm going to do it the mathematical way. Here we go. Displacement, delta x, is final position minus initial position. The place where I end up is my house. So my final position is 0 miles. The place where I started is my friend's house, which is at x equals negative 2.1 miles. Okay? Now, a negative subtracted becomes a positive, and so we end up with displacement is 2.1 miles. If you're wondering why I added that equal sign in the middle step, that just shows kind of consistency that I'm still working on the same problem. Nobody will get confused. Convince yourself by putting your finger at the starting place and the finishing place that my answer is correct, that your change in position really is positive 2.1 miles. Try it out. See what happens. Remember that on the chart up here, the positive direction is still to the right. That's where the arrow was on the left side. So keep that in consideration. Convince yourself the displacement is indeed 2.1 miles. If you can't do that, call somebody, text somebody, call me, text me, show up at class early tomorrow. Something like that. Alright, that's really the bulk of what we're covering. We will have a problem set in class tomorrow, and as you learned last time, the problem sets are super high level, so you want to definitely understand everything in here. Make sure you took those meta notes. You may have noticed I've been responding to a couple people's. I don't have time to respond to everybody's, but I do occasionally write notes on them. I am taking a look. That's it for this video. Have a good weekend, and see you on Monday.